In Chapter 3, we want to talk about how we can use numerical values to describe our data set. Oh, went too far. Alright, so in Chapter 2, we said, okay, there's three things we want to see in our data set. We want to see, okay, what's its center, how variable is it, and what's its shape. So in the previous chapter, histograms gave us a really good idea on the shape of our data set. So in Chapter 3, we want to see how we can use numerical values to help us explain the center and the variability. Alright, so the most common measures of center that we use typically are the mean, the median, and the mode. The definitions are here, but the mean is another name for the average, so you just add everything up and divide by the number of observations. The median is the middle value when you order your data, and the mode is the most common observation, so the one that pops up most often. Alright, so the easiest way to take a look at these is just to look at an example. So here's an example where they were trying to determine how UV radiation could affect hatching times for different amphibians. So here's a data set for 7 different species where they recorded the hatching time. So these are the observations. So the first observation was 6 days, second observation was 7 days, and so on. And I'd like to calculate those different measures of center for the data we have here. So the first one I'm going to do is I'm going to do the mean. So the sample mean, to calculate that, you're just going to do the sum of all the observations and divide by the number of observations. So here, you can see in the numerator, I'm adding up all my values. Denominator, dividing by the total number. So the numerator should add up to 51 divided by 7. So that's a mean of 7.2857 days. Now you'll notice here, I use this symbol, this little X with a bar over it. That is X bar. That is what we will always use to denote sample mean. Okay, so anytime you see that symbol X bar, you can know that I'm talking about the sample mean, and that's something we're going to use a lot in this class. So you'll get used to seeing that. Okay, the median. So for the median, the first thing I need to do, I need to reorder our data set and go least to greatest. This data set, we just pick the middle number right here. 6 is the middle, so that's the median. Okay, pretty straightforward. Now, if there was not a true middle number, then you would average the middle two, but I think we're going to see that in a moment when we get on to some other measures later. Okay, so the median is just that middle value. The mode is the most common. This data set has multiple modes, so you can either say it has multiple modes or it has no unique mode. Both of those answers would be appropriate here because there's no number that actually occurs more often than any other specific number. Now, one thing I want to think about though is what would happen if we sampled an 8th egg, and what if that egg took 28 days to hatch? Okay, so thinking about that, if you look at our data set, 28 would be a very long period for our data set. In fact, you might even consider it maybe what we'd call an outlier. So if I add in that extra observation, so now instead of 7 data points I have 8. So here's my original 7 added up. We tack on that next observation that took 28 days to hatch, and then we divide by 8. Well, what you're going to notice is that the mean is going to jump up to 9.875. Now, if we recalculate the median though, all I have to do is take my ordered data, tack on the 28 to the top of it, and you'll notice now I don't have a true median. There's no number right here in the middle. So what we do is we average those two middle values, which will average out to 6.5. So what I notice here is that the mean jumps quite a bit. Okay, it goes all the way from 7.29 up to 9.875. So pretty big jump. But the median hardly changed at all. And this is actually always true. So typically we say that the mean is very sensitive to outliers, whereas the median is not. I use the term outliers, and what we determine as an outlier in statistics is essentially any observation that's not representative of the population. So you might remember back in Chapter 2 we talked about distributions which actually have outliers built into them. Okay, we have those skewed distributions, and based on the shape of the distribution it changes which measure of center is most appropriate. Right? So what happens is, say here in our first picture, top left, when you have a right skewed distribution, what you have is you have built-in outliers up at the top of your distribution. They don't happen often. They're not very common, but they happen. And we just saw in the last example that those outliers, they're going to pull your mean up. So your mean is actually going to be pulled up above your median. Right? So your mean is going to be kind of inflated artificially. And same with less skewed over here. Okay? So in a less skewed distribution, your outliers are down here in this tail. And so your mean is going to be pulled down from the median. Now in a symmetric distribution, your mean and your median are going to be exactly the same. So we really like the mean. The mean is going to be really useful to us later in this course. So typically, if we have a symmetric distribution, we're going to stick with the mean. If you have a skewed distribution, though, that's when we're going to switch over and maybe consider using the mean as a more honest measure of censure. So in math, we often have the concept of something where we need to add up a lot of observations. So we simplify our notation. And the way we do that is, so let's look at this example. So consider you have some general sample, right? So the first person, maybe you're recording ages. So the first person's age, that would be x1. The second person's age, that would be x2, x3, on and on until, you know, the nth observation. So this is a sample of size n. There's n values here. Remember, little n, that's usually sample size. So if we were going to calculate the mean, first we would add them up, right? So x bar, right, remember that's the symbol for sample mean. We would add all our observations, the first, the second, and the third, all the way up to the nth, and then we would divide by the number of observations, which would be n. So what we use is we use this concept of summation notation to quickly show addition. So here, instead of writing x1 plus x2 plus xn plus dot 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 plus blah blah blah, we use this capital sigma. And this capital sigma tells me what I'm going to do is I'm going to add up all of these x values. So the sum of the xi's all divided by n. Alright, so that big sigma basically just means add a bunch of stuff up. Alright. So those are our measures of center. You have the mean, median, and mode. So now I want to look at some measures of variability. The two common ones that we use are range and standard deviation. The range is pretty straightforward. The range is just how far is it from your smallest to your largest value. And the way you calculate it is just take your maximum minus your minimum. So let's look at that days until hatch example. Right. So here's our data set without the outlier. So our original 7 observations. And if I want to calculate the range, it would be the maximum minus the minimum. So that'd be 11 days was the max, 5 days the minimum, 11 minus 5 is 6. So it's a range of 6 days. Now, the range gives us some idea of how spread out the data is, but what it doesn't do is it doesn't tell us how the data is sort of distributed within that range. Okay, is it all spread out evenly? Is it all condensed kind of in the middle? And so to get a better idea of that, we use what we call the standard deviation. So here I've given you the definition. The sample standard deviation of a data set, what it does is it measures how far on average the data is the sample mean. And the way to calculate that is using this formula. You'll notice that summation notation, that big sigma pops up. Alright. Now, if the standard deviation is large, that means our data is more spread out. And if it's small, then our data is less spread out. Okay. Now, this formula kind of seems pretty complicated and daunting at first. So I think the best way to explore it is to just use an example. Okay. So let's take a look at an example where we calculate the sample standard deviation. The best way to do it is I make a table. All right. So I'm going to use that data set, the days until hatch data set, where we were looking at how long the eggs took to hatch. And so I start by making a column of just my observations. So you'll notice in the formula there's this component of it that is all the little xi's minus x bars squared. So what does that mean? Well, it means you start with each of your data points, and each one of these, this is say x1, x2, x3. So I put all of my data set in the first column. Now, order of operations says the next thing I need to do is I need to subtract the mean from each observation. So the sample mean was 7.29. So in the next slide, I'm just going to take that sample mean and subtract it from each observation. So my first observation was 6. I'm going to take 6 minus 7.29. That's a negative 1.29. The next was a 7. 7 minus 0.29. That's a 0.29. 11 minus 7.29. That's a 3.71, and so on. Okay. So these right here, these are what are referred to as the deviations, right? This is how far the observation deviates from the mean. So these are our deviations. Of course, if you add all these up, you have some negatives, some positives. They're all going to end up probably canceling each other out. So what we do instead of just adding them up is we square them. And what squaring is going to do is it's going to make them all positive. All right. So I took each observation, I subtracted the mean. Now I'm going to take all those values and I'm going to square them. All right. So I take that negative 1.29 and I square it, and I get 1.6641. I take that negative 0.29, that deviation, I square it, I get 0.0841. And notice, if it's a number more than 1, it gets bigger. If it's a number smaller than 1, it gets smaller. This is nice because what it does is values that are close to the mean get penalized very little. See, this value is very close to the mean, so it contributes to our standard deviation very little. Whereas this value is very far from our mean, and it's going to contribute to our standard deviation a lot. All right, so I have my observations, my deviations, xi minus x bars, these. Then here, now I have all my squared deviations. So in the formula, it tells us we need to sum up all of those squared deviations. So now that I've taken each observation, subtracted the mean, and squared it, I'm going to add up all these positive values in the last column. And this is my sum of squared deviations. And that's what I'm going to take and plug into my formula. Alright, so here's the formula. It was the square root of the sum of the squared deviations over n minus 1. We calculated the sum of the squared deviations in the last slide. That was 41.4287. And then n is our sample size, so that would be 7, and we're going to subtract 1 from that. So we end up doing the square root of 41.4287 divided by 6, and you should be able to come up with about 2.6277. Alright, so the standard deviation here is about 2.6 days. So the actual process is a little bit involved. So one thing we do is we have another form of the standard deviation formula. It's a little bit easier to use, and it's called the computing formula. So you can use the formula that we just gave, but I typically use the computing formula if I'm going to do it by hand. Alright, so you'll notice in the computing formula we still have summations, but notice we don't have any deviations, so nowhere in here do I have to calculate the sample mean or subtract it from anything. All I need is here, firstly, I need the sum of the squared observations, and then I also need the sum of the observations, which I'm going to square afterwards. So let's try that with the same data set. So again, I use a table where I start out by listing all my observations. Those are my xi's, and then I list all my squared observations, so those are the xi squareds. Okay. So to get the sum of the xi's, I just got to add up all the original observations. And to get the sum of the xi squareds, I just add up all the squared observations. And so the sum of the x's, that's 51. The sum of the x squareds, that's 413. And then that's all we have to add up. We can go straight to our formula now. This is why the computing formula is a little faster. So the original formula says sum of the x squareds minus the sum of the x's, whole thing squared, divided by n over n minus 1. So sum of the x squareds, we just got that. It was 413. Sum of the x's, that was 51. N is 7, and n is 7 here. So you end up with 413 minus, that 51 gets squared, that's 2601. We're going to divide that by 7 in the next step, and 7 minus 1 is 6. Take 2601 divided by 7, you get this, and overall you end up with 41.4286 divided by 6. If you do that, you're going to end up with a square root of 6.9048, which is 2.6277, and you'll notice it's exactly the same answer as we got before. Okay, so the computing formula, takes a little less time, and it's also a little more accurate because you'll notice I tend to keep about 4 decimal places here, but notice I only had to round in one place, right? I only had to round right here with this division, whereas with the original formula, there's a lot more rounding going on, so you're a lot more likely to maybe be off by a few decimal places. So I tend to keep the computing formula. Now, you can calculate these standard deviations in StatCrunch pretty quickly, and if you're interested in learning how to use StatCrunch to calculate things like mean, standard deviation, some of the other things we're going to do in this chapter, you should check out my video tutorial, and that's in the video section of your My Stat Lab course. Okay, you can find the tutorial on there. All right. Okay, so the standard deviation, though, just like with the mean, the standard deviation is really sensitive to outliers. So just like when in a skewed distribution we said, well, really the median is a more honest measure of center, and so we don't really like using the mean. We also have the same problem with skewed distributions and the standard deviation. If you have a skewed distribution, the standard deviation is not the most honest measure of variability. It gets artificially inflated by skewness. So we want to explore some other options, and I want to start by talking about the concept of what a percentile is. So a percentile, you're probably familiar with percentiles. If you've ever, if you have children and you've ever taken to the doctor or you've ever taken a standardized test, they always report to you the percentile that your test score is in, or the percentile that your child's in. And what a percentile measures, it measures what percent of the population is at or below you, or your child, or whatever. So, as an example I gave here, if you take the SAT in high school, and your report shows you that you're in the 78th percentile, that means that you outscored 78% of students taking the SAT that year. Okay? So in statistics, we typically outline specific percentiles, and those are our quartiles. And so in the quartiles, we basically split our data into 4 parts. And so you take the first quarter of your data, that's the 25th percentile. That's what we call Q1. Then in the next quartile, you go another 50% up. Then that's the 50th percentile. You could call that Q2, but we already have a name for the 50th percentile. We call that the median. Then you go up another 25%, that's the 75th percentile, that's Q3. So basically we're cutting our data into 4 equal sections. The lowest 25%, the next 25%, the next 25%, and the top 25%. And then one way we use these quartiles to measure variability is we calculate the interquartile range, or what we know as the IQR. So the interquartile range, it's basically just the range between Q1 and Q3. So to calculate the IQR, we just take Q3 minus Q1. Okay, pretty straightforward. Alright, so what I've done is I've put up some data. This was a research company, and they observed the number of miles that we drive in America. So they randomly selected 15 Americans and observed how many miles they drove on a single car last year. And so here you go. So this person did 13.2 thousand miles, this one's 16.7 thousand miles, so on. So to get the IQR, first we have to actually get the quartiles. So just like when getting the median, we start out by ordering our data set, and then we actually calculate the median. All right. So the median for this data set is 12.2 thousand miles. All right. Now, once we have the median, now we can go on to calculating the quartiles. So what we're going to do is we're going to split our data in half. All right. So if this is our data set, I'm going to first calculate my lower half, and that's going to be all of my data up to 12.2. And then I'm going to record my upper half. That's going to be everything from 12.2 and above. All right. Now, to get my first quartile, all I have to do is take the median of the lower half. And to get my third quartile, I just take the median of the upper half. Now you notice here again, there's no true median. So I have to average 10.7 and 11.3. So my Q1 is 11. And then I have to average my middle two here in the upper half to get Q3 is the average of 13.6 and 14.8. That's 14.2. Alright, so I have my third quartile, my first quartile. Now we can calculate the IQR. So the interquartile range is just Q3 minus Q1. That would be 14.2 minus 11, and that's going to be 3.2. And what you'll notice is what the IQR does is it gives us the range of the middle 50% of our data set. Okay, so like in this example, the middle 50% of Americans, they drive miles, their driven miles only cover a range of 3.2 thousand miles. That's a pretty small range. So larger IQRs mean larger variability, and small IQRs show small variability. It's just giving you an idea of where that middle 50% is, right? Another way that we use quartiles is we use them to calculate the 5-number summary. So in the example I just gave you, the 5-number summary, all it does is it takes that Q1, median, Q3, and then it also reports the minimum at the bottom and the max at the top. So for the miles driven, the minimum is 3.3, the max was 16.7, and so the 5-number summary would be those 5 values put together. The IQR, it can also be used to test for outliers. And so one way we do that is we set up basically like a lower and upper limit on values where we think we should see data at. And the lower and upper limit that we tend to settle on, and this is basically based on empirical evidence, lots of data gathered over time, we usually say, okay, well, if you go from Q1 down 1.5 IQRs, and you go from Q3 up 1.5 IQRs, that gives us a pretty reasonable range where we would expect to see data. Now, if we see observations outside this range, those are data points that we're going to flag as potential outliers. So if you look at the data set from the driven miles in the US, we can go ahead and do that lower and upper bound. So for the lower limit, I'm going to take Q1 minus 1.5 times IQR. So our Q1, you remember, is 11. We're going to go down 1.5 IQRs, and our IQR was 3.2. So it's going to be 11 minus 4.8. That's going to give us a lower bound of like 6.2 thousand miles. So basically, we wouldn't expect to see many people driving less than 6.2 thousand miles in America. The upper limit would be Q3 plus 1.5 times the IQR. So that's going to be 14.2 plus 1.5 times 3.2. So that's 14.2 plus 4.8. And that tells us that we wouldn't, that's an upper bound of 19, so saying we wouldn't expect to see cars being driven more than 19,000 a year. That would be kind of an outlier. So this gives us our reasonable range, and if you go back to the data set, you'll notice there is one observation that's not in this range, and that was the person who only drove their car 3.3 thousand miles. So we would say that person is definitely a potential outlier. Alright, so that's how we can use it. That's one way that we also use the IQR, testing for outliers. Now, if you remember that big picture of statistics that I put up back in chapter 1, we made the distinction between population and sample, and the values that describe them, that are parameters versus statistics. So I want to just review so far what we've talked about. So for samples, the statistics we typically measure, so like the sample mean, we denote by x bar. The sample standard deviation we denote with a lowercase s. Whereas if we were talking about the population mean we typically denote with a mu, and the population standard deviation we typically denote with a sigma. Okay. So when we talked about percentiles, I mentioned those are measures of relative standing, but there is another common measure of relative standing that we use, and it's something we call a z-score, or a standard score. And the way you calculate a z-score, if you have a population with a mean mu and a standard deviation sigma, then the z-score standard score, it's going to be the observation you're interested in minus the mean divided by the standard deviation. And when you're calculating a z-score, what you're getting at here is you're trying to measure how many standard deviations are above or below average somebody is. So z-scores can be positive or negative. So negative z-scores mean you're below, the person or the observation is below average, whereas positive z-scores mean above average. So let's take a look here. So in this example, gestational periods in humans, they have a mean of 266 days and a standard deviation of 16 days. All right. So I might be interested in, okay, what if you have a pregnancy that lasts 40 weeks? What would be the standard score z-score for that? Well, first, we'd have to convert 40 weeks into days. So 40 weeks is 280 days. Then to calculate the z-score, I need to take the observation minus the mean divided by the standard deviation. So our observation, a 40-week pregnancy, is 280 days, minus 266, the mean, divided by 16, which is standard deviation. So that's 14 over 16. That's a 0.875. So this person is 0.875 standard deviations above average. We could do the same thing for a 37-week pregnancy. Okay, so a 37-week pregnancy, I don't know where that 48 came from. It's supposed to say 37. But a 37-week pregnancy, forget that, should be 259 days. So again, for the z-score, we take the observation, 259, subtract the mean, 266, divide by the standard deviation, 16. It's going to be a negative 7 over 16. And this is going to be your z-score, negative 0.4375. So notice the 40 weeks had a positive z-score, so you can interpret that as being, 0.875 standard deviations above average. Whereas the 37-week had a negative z-score, so that interpretation would be that that person is actually below average. They're 0.375 below average. Okay, so that's pretty much the main topics that you're covering in Chapter 3. What I would do is, if you're interested in saving yourself a little time in your homework, I would definitely go check out the tutorial on calculating descriptive statistics in StatCrunch that I've posted.